Welcome, everyone, and thank you for joining us for this Neo4j hosted Big Data London session titled Responsive, Robust Supply Chains Using Knowledge Graphs and Graph Analytics. Our presenters today are Dr. Maya Natarajan and Amy Hodler. Please feel free to submit questions throughout the presentation. There will be time allowed at the end of the session for a brief Q&A. With that, I'll go ahead and hand it off to Amy and Maya from Neo4j.
Thank you for the introduction, Marilee. Again, my name's Amy Hodler. I do all things graph analytics and data science at Neo4j, and I'm joined with my colleague, Maya Natarajan, who is our expert in knowledge graphs. So let's go ahead and get started. And I think you guys may remember just from this last couple of weeks, some news that hit about chip in the manufacturing causing quite a delay in the automotive space. And so you can see here, Ford had to reduce significantly the number of vehicles that they could produce because of their dependence on chips and the storage, or excuse me, the shortage in that area. And you can see here 2.5 billion hit to the bottom line, so pretty significant, all related to supply chain. And I think what I find interesting is one, this is terribly hard, and as anybody who is looking for a new car right now knows, there's a huge delay. But I like what Jim Farley said, which is actually they've learned a lot through this crisis, and they can more than just in regards to chips, that they can use this in other areas. And I think 2020 taught us that a lot. So there are a lot of things that happened in 2020. We had a lot of brittleness in our supply chains, and it helped us to reinvent the supply chains, but also businesses. I think there's also a lot of unintended consequences. So, these obscure dependencies that were surfaced, I guess I'll have to say the unknown unknowns. So we know more about what actually drives our businesses. And then I'd also say, low signal to noise ratio or too many haystacks and not enough needles. But that really gave us a sharp focus on optimizing for what was relevant at hand. And then I'd also say we have really felt the pain of having very perishable insights. So, and what I mean by that is data that we used became invalidated very quickly, or was continually shifting. So what that really pushed us to do is to be more responsive and creative. And I think more than anything, what we saw last year is just how closely and strongly connected we all are, and all of our processes are. So with that, I think I'd like to turn it over to Maya to talk a little bit more about some of the supply chain impacts.
Thank you very much, Amy. Just a little bit of background about myself. My name is Maya Natarajan, and I'm responsible for knowledge graphs at Neo4j, and really the impact it has across the various industries. All right, so we definitely know that the pandemic has been brutal, especially for the supply chain industry. And it's really for us to find opportunities from it. And this is exactly what our customers are trying to do. Now, this graphic is from our partner, Capgemini, and it shows us that about 65 to 75% of the 1,000 organizations surveyed here are facing challenges in all stages of the supply chain. From planning to sourcing to production to warehousing and distribution, and even in sales. So what are some of these challenges? In planning, it's the lack of information on impacted suppliers. In sourcing, it's the shortage of critical parts. And as we just saw was the case that Amy shared with us about Ford. In production, it's the inability to scale production up and down. In warehousing and distribution, it's the difficulty in balancing stock between warehouses. And finally, in sales, it's basically losing sales due to stockouts. Now, the one thing that all of these challenges have in common is that they're all complex, connected data problems. All right, when you think about supply chains, we know that these systems are heavily connected. They are heavily connected ecosystems of buyers, suppliers, service providers, multi-tier OEMs, IT systems, and many, many more. Now, the only way to reveal connections among dispersed, diverse data within a supply chain is by using graphs. What graphs do is that they create relationships between data And interrelationships create structure. So you see that graphs add context to data through relationships. Now, when you add context to data, you get knowledge. So that obviously brings us to knowledge graphs. So what exactly is a knowledge graph? It's an interconnected data set that has been enriched with semantics so that we can reason about the underlying data and use it for complex decision making. Now, every knowledge graph has 3 elements. The first element is data. And here we're talking about data such as structured data, unstructured data, and semi-structured data. The second element is graph. Now, when data gets ingested into a graph, relationships are added between data points, and that provides the first level of context. We call this dynamic context because when you take data and throw it into a dynamic structure like a graph, you get a structure that's connected contextually to all of its neighbors. And then the neighbors are all contextually connected to their neighbors. So the graph gets richer and richer as new information is added. So context is being added dynamically. Now, the third element is semantics. If you take data in a graph and then you add semantics to it, you get a knowledge graph. Semantics adds the second layer of context. So knowledge graphs have deep dynamic context. Now, the second layer of context is very important because this is how we make data smart, basically by driving intelligence into data so that we can infer meaning from it. Now, for those of you who are unfamiliar with semantics, it basically means meaning. There are many different types of semantics. We have controlled vocabularies like synonym rings, taxonomies, and ontologies. Synonym rings and taxonomies are lightweight, whereas ontologies are heavyweight, meaning they have better inferring power. However, ontologies take a long time to build and maintain, so we always recommend a minimally viable ontology. Next, we have entity resolution and analysis. Entity resolution is all about determining whether records from different data sources represent the same entity. Now, let's take my name as an example. Do Ms. Natarajan, M. Natarajan, and Ma Natarajan all mean the same thing? Well, of course they do, but this is not easy to do at scale. At scale, it's a very non-trivial problem. Okay, it means comparing every entity with every other entity and identifying it as similar or as a duplicate. Now, that's a tough problem to do, but it matters that we do it and we do it well. So let's imagine that you're in a business where consistency of data is key. You may have the question, do I have any clients trying to commit fraud, or am I able to detect if someone's trying to avoid paying taxes? Here, you'll need to know if an ID or a name is being used in duplicate, right? So entity resolution allows you to answer these kinds of questions, and that's why it's essential. Okay, third, we have tagging, categorization, and classification. And then finally, even AI is a type of semantics. Now, AI plays a very important role in a process called knowledge graph completion. This is a process by which missing entities and links are added to knowledge graphs. And typically in this process, the first step is entity resolution, and embeddings also play a very important role. Now, to store, manage, and analyze connected data, we need to use a knowledge graph. The Neo4j Graph data platform is a graph-native platform that supports both transactions as well as analytics. We have a graph data science library that's fully supported with fully supported algorithms and machine learning. And I'll be touching a little bit more on this in my next slide. We also have a visualization tool called Bloom for no-code graph exploration and investigation. Now, querying and analyzing your data in a graph database ranges from the basic to the really complex. So let's start off with the basic and work our way to the complex. First of all, let's look at queries. We use a Neo4j proprietary language Cypher to query the Neo4j graph database. Cypher queries are human-crafted queries with a human-readable result. Okay, the results of a query mean exactly what you expect them to be. And typically what we do is we use these for real-time matching when we know the data pattern of interest. But what if you don't know where to start the query or where to find patterns? Or if you want to find patterns anywhere in your graph. For this, you'll need algorithms, because you're really going from being local within your graph to going to a global graph. Now, algorithms are predefined formulas. They're used when you want to compute over the entire graph or subgraph, and you want to find answers to like popular paths or influential nodes. Now, the example given here is PageRank, and that gives you the most influential node. We have over 50 algorithms in our GDS library, and Amy will discuss these in greater detail as she walks you through a real-world supply chain example. Now, both graph queries and algorithms can be used to train machine learning models, specifically for feature engineering. But what if you don't know what to query or which algorithm to use? One possibility is that you use brute force and try out all the algorithms and then compare the results. But of course, oh my gosh, if we were to do this, this is one tedious task. Okay, so it's better to use embeddings. What are embeddings? These are this is a way of encoding the nodes and relationships into a structure that's suitable for machine learning. Now, the beauty of embeddings is that you don't need to know the pattern you're looking for, but keep in mind, these are not predefined like algorithms. So they're slower, and then they require more tuning, and you also have to tell it what attributes to look for. Now, all three, queries, algorithms, and embeddings, can be used for feature engineering and machine learning. And the question is, when do you use which? If we know what elements are predictive, we use queries and algorithms. If we don't know what elements are predictive, we use embeddings. So now, once you're done with creating these features, you can take these features outside of Neo4j and continue machine learning processing in other systems. Or you can use the features you've created within Neo4j, as we have graph-native machine learning as well. Now, what graph-native machine learning is it's computing machine learning tasks all within the graph database. Today, you can perform supervised machine learning within Neo4j, within the Neo4j graph database. What we do here is use labeled data to learn a function and to map input data onto outputs, all within the graph. This is exactly how we do supervised machine learning normally. The difference here is that we run supervised machine learning within the graph, taking relationships into account. So the question is basically, how does all of this tie in with the supply chain? There are many different applications of graphs in supply chain, and they break down into three different types at a very high level that we've shown on the left. And these three areas are supply chain optimization, logistics, and bill of materials management. Now, the specific use cases are actually shown on the right. Graphs are very good at handling these specific use cases shown on the right, because the supply chain is a highly connected ecosystem with lots of interdependencies. And graphs are the only technology that can handle these connections and interdependencies very easily. Okay, so let's look at each of these specific use cases. The first one is route optimization. Route optimization allows supply chain companies to find the shortest and the most cost-effective route between 2 points, taking various factors into consideration, such as drive, shift patterns, vehicle weight limits, and so on, to maximize efficiency. Graphs do a very good job of route optimization. Next, we have risk identification. Now, the typical approach for risk identification is to map out and assess the value chains of all the major products. Known risks typically can be identified and managed very easily over time. Unknown risks, like the pandemic, for instance, are very difficult to foresee. So reducing their probability, which is very tough to do, and increasing the speed of response, when these kinds of events occur. Now, this is definitely doable. And this is how companies can gain a competitive advantage. Okay, third, we have predictive fulfillment. This is all about predicting demand and shipping products even before they're ordered. It's a process that uses machine learning for predictive analytics, and that can be improved using graph technology. Fourth, we have quality recommendations. Now, in supply chain today, recalls are on the rise, causing severe negative impact, both in terms of profit as well as brand to a company. So it's really essential to be able to identify issues early in the chain, and also to be able to trace the root cause and source of quality issues and make the appropriate recommendations. And finally, we have supply chain driven product design. Now, this one's interesting. A product may be attractive for customers, but drive unnecessary supply chain costs for various reasons. It could be high cost of packaging or high cost of production, or as in the case of Ford, shortage with one of the components. So product design that takes all aspects of the business, especially supply chain, into account, could help companies be more responsive and resilient. Okay, so with this, I will hand over to Amy, who will walk us through a real-world example, real-world supply chain example that focuses on the first two use cases: route optimization and risk identification.
Thank you, Maya. And you can tell you've lived all over the world with the switch between route and route, which I love. So anyhow, let's show you a fun example. So this is actually an example of an actual customer scenario. We needed to anonymize the information and their name, or remove their name. But it's an interesting example of how you can use graphs to help bolster and have a more robust supply chain. In this case, the data is very typical of supply chains, which are shipping a lot of information, or a lot of information and product into different areas. You've got things like carriers, shipping sites, materials, distribution centers, customers, and then also just a ton of different relationships as well. Is in group of, has location of, ships to, or shipping carrier. But there was just too much of that for me to list on. So kind of I think the typical information you'd expect in a supply chain. And the very first thing that this customer needed to do is just to understand their supply chain a little bit better. And once you have information in a graph, there are queries you can do to kind of look at what's the shape of my graph, what is my supply chain, potential indicators of problems. And I would call these deceptively simple queries, because you can ask things like, what is the depth of my supply chain from different starting points, which can actually indicate more vulnerabilities, or things like if vendor X is unable to operate, how many stores that I ship to are impacted. Now, these are deceptive because it's a very simple question, but it's deceptively simple because these questions are open-ended questions with variable lengths. So you might want to say so many hops out, or between 2 and 8. And so you have this open-ended, we do not know what we're going to have to do to put these together. And that can be very difficult to do with a relational database system, especially if you have to go and do many lookups or joins. So if you've worked in these kind of scenarios where you have to do a table lookup, then you have to join items, and then you have to do another lookup and another join, you know very quickly how complicated and slow this can get. And so there's just the feasibility of that. And then there's also a speed aspect. So graphs are really good at traversing hierarchies up and down. And so you might want to say, what are the alternative vendors, if that one goes down, that are similar to that particular vendor 4 hops out, so not too many hops out. And most of you probably recognize once you go beyond about 4 hops for indirect relationships out, it can be very difficult to do that with any regular speed in a relational system. So just getting started with that was helpful for them. And then they moved to graph data science, and the graph algorithms. This is a little bit of a brag slide, in that we've got about 60 very robust algorithms that are fully supported. Things from pathfinding and search, so finding those optimal routes, are very relevant to this scenario, but also things like centrality and importance. What are the influencers, and what are the most important nodes in my network? community detection. How are things grouped together? How, if I need to partition, where can I partition my graph, and where can I partition my data? Link prediction. That estimates, at least this type of link prediction, it's a heuristic link prediction. It estimates the likelihood of relationships forming in the future, or estimating missing information. Similarity, how alike are things compared, doing kind of like a set comparison. So how are individual nodes more or less alike? And then graph embeddings, as Maya talked about, basically understanding the structure of your data itself, your graph, your network, and then smashing it down into a format that machine learning can actually do things with. So again, the next thing this customer wanted to do was actually start to get in there and do some algorithms and find some interesting things. In this scenario, they were trying to optimize their route and do some risk planning. And so first, they wanted to say, well, what are the optimal routes and what are the alternatives? What are the costs of those? And then they wanted to compare that to the routes that were actually taken. And looking at that, they started with, of course, their graph, and they started with what's called K shortest path. Now, they could have just said, give me all the shortest paths between A and B, or between all pairs, but that would have been very tedious and more information than what they needed. So they used K shortest path, which looks at the shortest path based on a weight, in this case cost, and they can say, well, what's the top 5? K just means the number, so you could have been 5 shortest path, 8 shortest path, whatever you wanted. And then they said, okay, well, what are the costs of these? And in this case, cost is just a fixed cost per mile that they have, but you could pick time if time was more important. So whatever that cost on that relationship that you wanted to add. Now for this customer, it was very interesting in that they found that often the next best option, the top 5 in their case, were not chosen. And so they looked at what their drivers were doing and what were the least cost routes, and it gave them something to then investigate. Like perhaps it's road preference because of the quality of the road. Maybe it has to do with familiarity. So right away they could look at ways to optimize their routes, in particular as they were performed by their drivers. So next, after doing that, they wanted to look at, well, what are my critical points of risk? And what's the impact to customers of those risk points? And so they then used another algorithm called centrality. And they were looking at, and centrality basically, in this case, betweenness centrality, looks at, it finds bridges between groups. And so it looks at the number of shortest paths going through any particular node, in this case, a distribution center. So what distribution centers have a high number of shortest paths going through them, and in that way that they're very important to the overall network. And they identified several as either bottlenecks. Let's say if Christmas comes up or some holiday and they have to ship a lot of whatever the product is, or if one were to actually go offline, they weren't able to ship, which ones are the most vulnerable. So they used betweenness centrality for that. And then they used degree centrality to look at the centers with the most incoming and outgoing links. And so what that really is, which distribution centers have the highest use. And so degree centrality just counts those in and out links, which in this case was just those routes between distribution centers and retailers. And it sounds really simple, but you can actually learn a lot in this case. So what they did is they included weights onto the incoming and outgoing links, and the weights represented the number of shipments that went. So, one link between a distribution center and a retailer, and then how many shipments a month were going through that. And so they did that, and then they started to say, well, wait, we've got directions on these. And so with degree centrality, as well as the other algorithms, you can also look at the direction of the relationship. So in this case, they looked at first at outgoing direction, and they could say, hey, this distribution center has a really high centrality score if I look at the outgoing to customers. And so if this center goes down, it's going to hurt customers more than if another one goes down. And then they reversed it as well and did incoming. And so that would be shipments inside of the supply chain. So from distribution to distribution center to other distribution center. So what's the impact in this case? What's the high impact going out, and then high impact between our own different supply flows. So pretty interesting things you can do if you tune those algorithms just a little bit for different scenarios. So then what they said is, okay, we know which points are high risk, both for our customers, big customer impact, and then we also know which ones are high risk for our internal working of the supply chain as well. And so, of course, what do you want to do? You want to find those alternative distribution options for high risk routes. And you could just go back to that first K, shortest path. So the very first option we looked at is like, hey, just go to your alternative. But what happens if you don't have a natural alternative? Like, I do not have a path between this distribution center if it goes down and my retailer customer that I have to ship to. In that case, what they started to do is they actually said, well, let's look at similarity between distribution centers. So in this graphic here, we are looking at the similarity of attributes. The yellow node is the distribution center that was a high risk, that had a high impact, and they didn't have any other direct supplier or distribution center that could pick up the slack. But what they did is they said, well, let's look at the other distribution centers, in this case, green, pink, and pink, that have similar customers, so similar end retailers. And so there was overlap there. And so in this particular case, if there was a disruption with the yellow distribution center, they already knew ahead of time, and they talked to the green distribution center ahead of time and said, hey, if we get an overflow situation, or if we have more than we can handle, or there's an interruption, can you help us take some of that overage and deal with it that way? So really interesting. With I've just shown even just 4 of those 60 algorithms, and show how you can get a lot of value there. Now, what they're looking at doing next is actually using that graph feature engineering and machine learning that Maya talked about earlier. So if you think about feature engineering, basically you're combining data to create more meaningful features for use in machine learning. So predictive features are what we're trying to get here. And so using graphs in this example, what they were looking at is, how do I combine influential components? So components in things I'm packaging together. I want to know what's influential for whatever reason. And I want to combine product attributes. So maybe in this case, you have products with different components, and they have different lag times in either when they arrive from when you order them, or they just take longer to package. Maybe there's an assembly process that has to go in. And you can combine those graphy and those non-graphy features, and then use that in machine learning. And you can combine those. You can see here the table in the middle. You just take those graphy elements, the scores, some of your non-graphy elements, and then you pump them into your machine learning process. You could also use graph embeddings as well. So I've shown those here in the middle. But what's interesting here that I've always found, all of our research and our customers see every single time, that when you combine graph elements like relationships and page rank scores, and non-graph elements like long lead time, you actually get better results than using just one or the other. And so you don't need to throw out what you're currently doing. Instead, you should just add those relationships in to improve your overall results. So Maya talked a little bit about the graph native machine learning workflows inside of Neo4j. So I just wanted to show you what a workflow would look like. Basically, you would do your feature engineering, queries, algorithms, embeddings. You would use those as input into the training option. So it's just train.node prediction kind of thing. And you basically do that. We handle the train test split. We also handle the model selection and the model scoring. So you get a result with the model that scored the best. And then your option, you have multiple options at that point. You could either apply it to what you're currently doing and predict a node, a package is likely to delay, or you could do something like predicting missing information. Like, I think there should be a relationship between these 2 items that aren't there. Or you could store it and use it later, and publish it and use it with your other colleagues. So the reason why people use relationships in machine learning is that we know over and over again, like I said, the research shows that relationships are highly predictive of behavior and complex outcomes. Now, Traditional machine learning tends to ignore this. They ignore the network structure because it's difficult to extract that structure in a way that's usable for machines. They need a low dimensionality. It's more difficult for machine learning to understand that. But because graphs are based on networks and relationships, you're able to basically take that information and use it for machine learning and predictions you otherwise wouldn't be able to. And so, like I said, I think on the last slide or before that, you don't have to stop your machine learning pipelines. You just get to add in the relationships that are already there and you're not using. And I don't know any data scientist who says that they have too much information. So use the information that you already have. And so with that, I think Maya's going to talk to some case studies and talk about our customers.
That's right, Amy. And I just couldn't figure out whether to say route or route.
Use them both.
I know, use them both. Anyway, yes. Well, we have over 800 customers at Neo4j who are utilizing graphs for everything from detecting fraud to real-time recommendations to risk and compliance, just to name a few. Highlighted in the middle are some of our supply chain customers, such as Daimler, Volvo, Levi Strauss, and Airbus. I'm now going to actually walk you through 4 customer success stories. All right. First, we have Lockheed Martin. The challenge at Lockheed Martin was that they wanted to integrate all of their processes and data all the way from engineering to ERP to procurement across the entire life cycle of their highly complex products. And there were 2 issues. One was to determine how to connect data across their disparate data storage systems. Basically data was in various silos. And second was to see what connections there were amongst the data from these various systems. Okay, so without this visibility into the entire product ecosystem, there was no easy way for them to gauge downstream impact of a single variance. So the solution, they deployed a Neo4j knowledge graph, and they used it to perform an impact analysis to determine the downstream result of an issue or a change anywhere in the product lifecycle. So basically identifying all the things that could have influenced a product part and what caused it to fail. They use Neo4j to do things like traversals and find variance in the process and report it back, thereby significantly optimizing dependencies and increasing efficiencies. All right, next we have the US Army Bill of Materials Management. Now here their challenge, tracking parts, orders, and their connections to systems, components, and subcomponents was a significant logistics challenge for the US Army. Army leaders basically needed to be able to forecast the need for replacement parts, calculate things like mean time to failure rates, answer what-if questions like the cost of deploying certain forces and their supporting equipment to a new war zone, for example. So what did the US Army do? They deployed a Neo4j knowledge graph that has provided them total visibility and tracking of costs in the system. And they've realized 2 significant benefits. One is ordering and replacing parts is quicker, cheaper, and more accurate with now than it was before. And secondly, complex analysis is 7.5 times faster, allowing for more agile responses to scenarios. Thirdly, we have Caterpillar. Caterpillar has combined a Neo4j knowledge graph with machine learning for proactive predictive maintenance to improve equipment lifespans. So here in this process, millions of warranty and service documents are parsed for text and added to a knowledge graph for context so that machine learning models can learn prime examples and then anticipate required maintenance. This proactive remedial action has saved them downtime and increased productivity. And then last but not least, we have Boston Scientific. At Boston Scientific, the challenge was that they had difficulties finding at-fault components in the manufacturing of their products. And they have a lot of products that include things like stents, pacemakers, artificial heart valves, and so on. Their solution was that they used a Neo4j knowledge graph to model and analyze their complex products. Using this knowledge graph, Boston Scientific can quickly, and here I mean really quickly, they were in the order of, from the, they're in the order of minutes, and they reduced it down to seconds. So they quickly pinpoint components that were most likely to fail. In addition, using graph algorithms, specifically the shortest path algorithm, they can now identify and eliminate bad combinations of components. So I will hand you back now to Amy to wrap up.
Great, I get to bring us home. So if you're not already familiar with Neo4j, we think of ourselves, we are the connected data company. We were the creator of the world's leading graph database, the first graph data science platform, and I would still say the most awesome graph data science platform, the most flexible graph data model, which is a property graph model, and the easiest to use graph query language cipher. So as Maya said, thousands of organizations worldwide using Neo4j, 76 of the Fortune 100, 7 of the top 10 retailers, 7 of the top 10 software vendors. You've already seen some of these logos, but definitely spans the spectrum of different industries as well. So we've talked about a lot of things. Oh my goodness, lots of resources for you here. All of them on neo4j.com. You can download these slides. We'll make them available so you can click on some of these that we think will be more interesting to those of you interested in supply chain. And then with that, I want to thank you for your time, and hopefully we have time for a few questions.
Great. Thank you both, Amy and Maya. That was such an excellent presentation, so informative. And I have to say, I kind of bounce back between root and route myself. I think that might be a
I'm not going to be.
I
was just going to say this.
Oh, go ahead, Maya.
No, I was just going to say I'm not going to be allowed to forget this in a hurry.
Well, we have had some questions from the audience, and I want to remind the audience that they'd like to submit a question. They can do so by typing it into the questions tab. But here's one. I think it goes back to when Amy was talking about the algorithms. I believe it was the brag slide. And the question is, are the algorithms you showed the ones that are most often used for supply chain?
So we always get a lot of questions on which algorithm should I use for this or that, or which is the most popular algorithm. And I really think it depends on your data, of course, and the kind of answer or prediction you're trying to make. So for example, centrality algorithms, we showed 2 of them, degree and betweenness, and those are all about finding influential nodes, but they all have a interesting history, and they come from different disciplines. So how they define influence is very different. And so a great, if you're looking for a resource to get started, there's the Graph Algorithms book, which goes into more detail on many algorithms, but we also have in our docs, we also have quite a bit of background on each of the algorithms, so you can understand what they were created for, how they define things like influence. And we also have a chart after each algorithm in our docs that says, you can use them with weights, or maybe some of them can be used with weights. And so it also says, what type of data you can use them on. So I'd start with those resources.
Great, thank you so much. And here's one, I'm not sure what it was referring to. So it's asking, so you're actually doing machine learning inside of Neo4j now, and what types of machine learning?
Yeah, so yes is the short answer. We are doing graph-specific machine learning in the platform, which is focused on node classification. So is this a good part? Is this a bad part? And that's a prediction. And link prediction. So is the distributor likely to order a specific product? That would be a relationship. So those are the 2 types of very graphy machine learning that we do inside. But I just want to be really clear that we're not trying to do a general purpose machine learning. So we are not trying to be TensorFlow or PyTorch. There are plenty of good tools out there for that type of information. But if you want to predict very graphy information, node classification, link prediction. Doing it with inside of a graph is often very fast. It often provides just a lot of options. And if you're going to be updating your graph, then you don't have to leave your graph and come back. You can stay within one platform.
Great, thank you for that explanation. It looks like we have time for maybe one more question. And here's a big question, so I like to ask this one because it comes up often. So if you're just starting to look at graphs, how should someone get started?
I'll take this one. So basically, I would say I have three main things that I point out whenever I have to answer this question. And I would say the best way to get started is to look at our Sandbox. And you know, the resources page here, we have Sandbox. We have the link to Sandbox, and it's you know, it's a great place for developers and data scientists because it gives you a place to play and just test things out before you know, and figure out how things are going to work. The second place I point you to is connections. That's also we also have a link to that here on this page. And you know, here we have this connections was specifically for supply chain, but we have you know, where there's some great sessions, and we have customers who have actually showcased how they've deployed knowledge graphs. So I'd like to point you to that. And the third place, of course, is neo4j.com, our website. We have a ton of information on our website, and you know, it's a great way for anyone who doesn't know anything about graphs to get started and get going. And before you know it, let me tell you, you'll become a graph expert.
Oh, excellent. Thank you, Maya, for all those resources. That's great. And I want to thank you both for your time. That was an excellent session. It was so informative. So thank you, thank you, thank you. And also thanks to our audience for joining us. And with that, I'm going to wish you all a great day.
Bye.